Take a look at this problem right here because it's a perfect example of an exact differential ODE, and that's probably the easiest to solve. The form of a exact differential ODE is going to have something like this. You have f of xy, f of xy dx, plus g of xy dy equals 0. So from this problem, we can see that f of xy, which is going to call it f, is going to be 2xy. And then we can see g of xy is going to equal x squared minus 1. Right there. We need to prove if the partial differential of f with respect to y, because you're trying to go the opposite of whatever the differential was, so dx, so we're going to do y, has to equal the partial of g with respect to x. So the partial of f with respect to y, we can see is just going to be 2x. And then the partial of g with respect to x, by using power rule, is also 2x. So they equal each other, which is good. So that means you can use the following, as long as you have the exact differential, like this condition is satisfied, you can go along with the following. We also know from our notes that f is equal to the partial derivative of u with respect to x, and g is a partial derivative of u with respect to y. So we're gonna integrate both of them to find u of xy. So for the first one, we're going to say u equals the integral of 2xy. Since it was dx, we're going to put dx. And then we're going to have an addition of a constant of the opposite, so fy. And that's going to equal, we can do the math with dx is going to be x squared over 2 times 2 is just x squared. So we get x squared y plus f of y. And then now we can do g, and we end up getting u equals the integral of x squared minus 1 dy. So now it's different. And of course, our constant now is going to be g of x. So that's going to equal, if we do it with in terms of y, we can get y x squared minus y. Right? And then plus g of x. Okay. Basically, you want these to equal each other. Keep in mind that this is the same thing as that. See? X squared y, I just wrote it backwards. So, if we make these two equal each other, we can say, because u equals u, x squared y plus f of y equals, and we're going to write this as x squared y again, minus y plus g of x. And of course, we can cancel out these terms. So we have one right there, have one right there. So we say f of y equals negative y plus g of x. Okay, so of course, we could say f of y equals negative y and g of x equals 0. And that would definitely work. But one other way to prove it is if you say this right here. Let's go in light blue. Well, we know that g is the partial of u with respect to y. So what we can do is differentiate one of them. We can differentiate this right here with respect to y and make it equal to g. So we're going to differentiate the one we already did with respect to x. Or with respect to y, we end up getting x squared and plus f prime of y, like that. So once we make this equal to g, it's going to equal x squared minus 1. Okay, you can cancel these two terms out, x squared, so we say f prime of y equals negative 1. Then integrate both sides, and don't worry about the constant in this case. We end up getting f of y equals negative y. Okay, so that's proven. So since f of y equals negative y, then g of x has to equal 0. So then what we can do is plug them in, and notice how u is going to equal the common term, and then we just put these in place. U of xy equals x squared y, and then we have a minus y, which is the same as the f of y, and then plus a g of x, which is 0. So see how that makes these two equal each other. So we say x squared y minus y, and that would be your final answer.